नमस्कार, विज्ञान परिचर्चा में आपका स्वागत है। एक नए विषय के साथ आज पुनः उपस्थित हूँ। आइए चर्चा करें। नमस्कार। Hello everyone, how are you? I hope you have gone through my previous PPT. So, in continuation to the previous discussion, we are going to discuss about corrosion measurement. So, if we recall our previous discussion, we have talked about what do we mean by corrosion measurement and what kind of tools we can use for corrosion measurement and analysis. So out of which, sorry, we have talked about weight loss analysis and calculation of corrosion rate. Today we will switch to the new topic that we have already introduced in last discussion. This is basically the surface analysis. So we can say the second approach, and in which we may consider following techniques: optical microscopy, scanning electron microscopy, atomic force microscopy, and sometimes we also use scanning tunneling microscope. But if we do the analysis using these techniques, whether optical microscope or SCM, we have also mentioned here basically TEM, that is transmission electron microscope. Then the next one is atomic force microscope and STM. So today we'll talk about these two techniques, or you can say the three: optical microscope, then scanning electron microscope, and transmission electron microscope. These techniques are very good, can give very accurate and logical information. However, it depends what we are trying to see. So that's why we can say the information is good, but not sufficient to make any final conclusion about corrosion, because this is a kind of subjective approach. Therefore, if we would like to analyze the corrosion, we also need to include some other technique along with surface analysis, either using by optical microscope or SEM or TEM. So optical microscope is, I think everybody is familiar with this technique. I think you have already gone through few measurement in physical metallurgy lab. So I'm not going to talk about optical microscope, but in general it has two functions. One, at least we can illuminate our specimen so that we can get very good quality picture, or we can visualize this properly, and then it can create a magnified image of any sample or specimen. So the principle you already know basically, and how it works. Basically, its working principle is the interference of the light. You have two lenses, objective lens and eyepiece, and then you can create an image, and where which can get the information particularly about the surface roughness and the shape of the specimen. So if we'll say what is the scale we can go, so in general, if we are talking about your lateral, then we can go some millimeter to close to micron. And if we are talking about the height analysis, then it can be micrometer to some of nanometers, let's say 500, 600 nanometers. We can resolve by doing the optical microscopy. Here we can see the one example of the surface analysis using optical microscope, and the corrosion which basically form the pits. You can see one pit formation is here in the picture 1. Right side picture you can see the pit formation. So what we can see here, we can see at least what kind of morphology is there of the pit. Similarly, what is the size of the pit. Here also the morphology is not circular, it is something elongated, and then size. So even we can say this is the having a smaller size pit. In this case, this is the larger size pit. So these kind of information can be extracted by using optical microscope. Now let's go to the other technique, that is electron microscopy. So before talking in detail, let me give a brief understanding why we are going to use electron microscopy. See, you are already aware about the Rayleigh criteria that basically decide what is the minimum distance between two objects that can be resolved by a light. And if you remember that formula, so resolution limit basically depend upon the wavelength. So it's order of the wavelength. So if everything is very ideal, let's say we have no aberrations, all the lens, all the assembly is working 100% correctly, and as per the theoretical understanding, it's basically working as per the theoretical limit. Then we can say your optical microscope can resolve up to the wavelength of the visible light. So what is the wavelength of the visible light? Everybody knows, like 300, 400 to 600 or 700 nanometers, right? But we are aware like there is some corrections always there. So whatever microscope we can build, even the best one, we cannot go more than 400 to 500 nanometers due to the theoretical limitations. So if we are further willing to go to resolve, let's say 100 nanometer, 50 nanometer, 10 nanometer, or even lesser than that, then our optical microscope is not useful. So then people have came with the idea like we can develop the electron microscope. Idea was similar as in optical microscope. In electron microscope, rather than using optical light or optical wave, we can use the electron wave, because you know if electron is moving, it also behave like a wave. We are aware about the wave particle duality. So if we apply a very high potential across the two electrode, and if we have one source of electron, then you know electron can behave as a wave, and then this wave can be used, and we can fabricate the microscope similarly as in optical microscope. So same concept has been utilized, and if you remember, if you calculate the wavelength of a moving electron, that is lambda, by using lambda is equals to h cut upon mu, or momentum. So if you really use that relation, so you can calculate, if you are using, let's say 10 kilovolt or 5 kilovolt, the wavelength will go almost close to angstrom. You can do the calculation basically, but I'm just giving a rough data, right? So if we are going to calculate in such a manner, so if we build a microscope, then of course we can resolve the nanometer scale easily in angstrom scale also, and that is the size of, close to the size of the atoms in angstrom. So that was the principle. And what kind of, so I already talked about like scanning electron microscope and transmission microscope. And using these two techniques, we can get variety of information, such as we can identify the cause of corrosion. Cause of corrosion means how it started, what was the basic reason to start the corrosion, like. And similarly, we can also understand the thickness of the material. We can calculate the surface layer or any coatings are there. We can also identify if there is any fracture of the surface, and what kind of fracture is there in the surface. Then if any extra atom or extraneous element is there in the surface, that kind of information can be easily identified or extracted using electron microscopy. So now we'll go one by one. Let's first discuss about the scanning electron microscope. So both the systems are having almost similar architecture. Slight differences are there about how we are going to take the signal or how we are generating the image. So here you can see a basic block diagram of scanning electron microscope setup. So as I said earlier, we need to have one electron source. So they are depicted in this electron source. Generally we are using field emission, like field emission based electron source, or sometimes thermionic also. Then we have one anode. Why anode? So anode is required to give a potential. Your cathode will be a zero potential. So based on the anode, we can understand what is the potential across the electrode. Then your condenser lens and objective lens, similar manner as we are having in optical microscope, to control or to focus the beam. Then since the word is known as scanning electron microscope, what do we mean by scanning? Scanning means we are basically looking one point to another point, and then we are going to look out entire surface. If I would say, if you see my hand here, so let's say we start with this point, go with this point, then come back down, this, like we are just scanning entire surface. So this is the scanning coil. So scanning coils, what is the role of scanning coil? Basically, it has to focus. See, it has capacity to focus entire this region by using our objective lens as a condenser lens. But the problem is that scanning coil can focus in each area. So you can get the information of each area, then assemble this together, and we can get the information of entire sample, right? So what will happen basically, it will interact with our sample after objective lens and then generate some kind of secondary information or secondary data, and this entire basically system is enclosed in a vacuum. So interaction of electron with the sample creates different type of electron, maybe photons or irradiations also. And particularly we focus on two types of electron. One is secondary electron and another is the backscattered electron. So let's say this is our upcoming beam. Here this is our sample. If you see the cursor, this is the sample. Beam is interacting here. So this is the interaction value, the quality of the picture, and your resolution. Many things will depend upon the interaction value. So this is the interaction value. So here you will get the secondary electron, as well as we are going to get the backscattered electron and then some photons. Okay. So what is the secondary electron and what are the backscattered electrons? Backscattered electrons basically, they are just having some interaction with the material and may lose their some energy and then just leave out the surface. So the same electron just scattered through the material. But the secondary electrons are basically those electrons for those who are basically regenerated. The first time of electron is absorbed by the material, and then material emit the secondary electron. So that is the regenerated or re-emitted electron from the material. So we can consider the intensity or the amount of these electrons and the energy of these electrons, and we can generate the image. So let's say there is a change in the interaction value, there is a change in the surface morphology, top and down. Then of course there will be change in the intensity or the density of these electrons, and that can give a different signal, and then we can create a image. So we are having these two kind of electron, and by using secondary electron we can get more detail about the topography or the surface information, like up and downs, or the what kind of shape and size of the system. That information may be acquired, and will be more, you can say, resolution will be little better. And basically backscattered electrons are more better about the compositional information. Let's say you have material which is, it's a compound, so you have 2 or 3 different kind of metal mixed together. So it can give the information like in which zone or which particular regions one kind of metal is there, in another region what kind of other material is there. So that kind of compositional information can be extracted by using the backscattered electrons. Okay, so this was about the how the SEM works and what information we can get. To get slightly more detail or better understanding, let's say I review 1 or 2 paper which is recently published. So here one example is there. Let's say we are going to talk about this article, effect of small content of chromium on wet dry acid corrosion, behavior of low alloy steel. So how, if there is a change in the chromium concentration, then how the corrosion behavior will change in steel alloy, right? This paper is published in this journal, Acta Metallic Change. So what is the sample here? So the test steel and the corrosion test in the sample was chromium content was 0.10 to 0.50 weight%. So basically they have this variation in the chromium content, and overall sample we can see the chemical composition of the samples. So see the chromium 0.1, chromium 0.2 and chromium 0.5, and then respective your carbon, silicon, manganese, sulfur, phosphorus, copper, nickel, chromium, and then valence iron. So remaining is the iron, what the percentage of iron is there. So basically we are having a 3 sample, 1, 2, and 3, that they are going to analyze. And what was the size, like when we are doing the measurement? So they have prepared the specimen. The size was 60 mm, 25 mm, and then thickness is 5 mm. Then how was the measurement? So before doing any measurement, they have also done the polishing by using the 600 grade silicon carbide emery paper, so that surface becomes smooth, so that they can look out the phases or any, basically the you can say the grains and granular structure. Then the specimen was cleaned in acetone and alcohol, and also they have gone for the weight analysis, so weighted by an electronic balance, and which are having very good accuracy. So here you can see the optical image. So this is just microstructures of the tested steel, and you are having first sample. So this is not corrosion. Before corrosion, how our sample look like, because they have 3 different composition of chromium. So they fabricated like this way. There is a differences in the microstructures if you look clearly, and even there is also the difference in the distribution of the element, that roughness if you can see here as compared to this. Here also it's look like little bit more uniform as compared to this. So like phases are not very uniform. Here the phase, and see the phases here not very uniform as compared to this sample and this sample. So these two samples are relatively different, and they have concluded like the microstructure of 0.50 chromium are finer. So in this case are finer. Finer means smaller than that of 0.10 chromium steel. Then what kind of corrosion analysis they have done here? So this is the corrosion analysis chamber. So this is a kind of a cell which is having a two compartment. Here they can record the temperature. Here they can also record the temperature. There is a gas inlet, and this is the filled distilled water, and this is the sample holder. So sample is not in the direct contact of the liquid, so that's why it's wet and dry, and gas inlet is there, so they are basically inserting the oxygen, sulfur dioxide gas, and in this case this is basically distilled water. So water bath is there, so sometimes the condensed water is also going up, and this drop is there, so that's why we are calling it, if you see the title is wet and dry acid corrosion. So the acid gas inside the test is having 4 value percent oxygen, 13 value percent CO2, 500 ppm S2S, and 100 ppm SO2, then balance of nitrogen, and is continuously put into and flew out of the container. So this is the gas in, it's creating some bubbles also, and then this is the gas out. So this is the setup, basically setup. Gas is going like this way and then going out from here. Okay, so this is the overall setup. So inlet, outlet, so you are even having the two samples, and they are going to analyze what kind of effect is there. And the gas flow rate is 100 ml per minute in first 24 hours. Then they have slowed down the flow rate. It's only 10 ml per minute after 24 hours. And sample was kept at 50 degrees Celsius for 19 hours, then 25 degrees Celsius for 3 hours, and then transition time between 50 to 25 is 2 hours. So basically, when they are reducing the time, so it takes almost 2 hours to reduce this temperature. And this is the generic. Then how long the sample was kept there? So they have basically investigated different time interval like 7 days, 21 days, 35 days, 49 days, and 98 days. Okay. Now we can see here the output. So there are many other analyses they have reported in this paper. If you are interested, please, you can just follow this reference. So what we are trying to see here, like when we have 3 samples, as you see earlier, the change in the chromium concentration, how the rust look like, because it's iron and it will rust due to the fumes and vapors. So what was the analysis? If you see here, the morphology is not exactly same, and even they are not have done very high resolution imaging, but still it looks, the morphology of this surface and this surface is different. Even the formation of this rust is also slightly different. And what they have analyzed, they found that from micron size acicular rust to nano size flocculent rust, means when the concentration increase of the chromium, so it was 0.1 to 0.5. Chromium was changed like this way. So when it is increased, there is a change in the micron size rust to the nano size rust. So first of this, change in the size, micron to the nano. So rust even just change. Also there is a change in the shape or the shape. So shape is earlier it looked like some kind of needle kind of particle, which is having some needle kind of outlets structures, and this is more kind of loosely packed just particles. And the grain size of the rust is also decreased when we are having higher concentration of chromium, and also the reduce the amount of pores and the crack in the rust. So in case of lower concentration of chromium, the cracks are slightly higher in the rust, and also they are having some pores, which is basically reduced once we are having the higher concentration of chromium. So this was one analysis based on the SCM, that what is the size of the rust, or you can say the byproduct of corrosion when it is your material is exposed in a environment such as some gas as well as the vapor. Similarly, there is a change in the morphology of this rust material, and also they are having pores and crack formation. So these are quite sufficient information which has been analyzed just using SCM. So we can understand like how the SCM can be used to analyze the corrosion in a metal or metal structures. Let's say another example which can give the idea about the analysis of SCM. So this work was published in 2015, Engineering Failure Analysis Journal, entitled as Investigation of Stress Corrosion Cracking. So basically this is again corrosion cracking due to the stress. This is the analysis. So stress is there. We are going to apply the stress and then some environment, and going to analyze the stress corrosion cracking behavior of super 13 chromium tubing by full scale tabular good corrosion test system. So this is what is the meaning of full scale tabular good corrosion test system. It's inbuilt system. They will explain later what kind of system is there. So if we say what is this, so a self-built device called full scale tabular goods corrosion test system was used to test a 6-meter length. So basically it's a 6-meter long, 13 chromium built tubing with coupling. So it's having one tube with other to study its corrosion performance in spent acid. Spent acid means a mixture of acid or something else. We'll discuss later in the article. So what is the structure? So here you can see what we mean. What do we mean by full scale tabular good corrosion test system? So see here, they have one pipeline which is having another pipeline inside, and so this is the interior structure where they have one pipe which is coupled here together, and top of that another structure is there in which we can have a gas inlet, liquid inlet. Similarly, here we can have liquid and gas outlet, and then we can having a tensile force also. So see, they are applying a tensile force here. Then how the tensile force is going to affect the material corrosion behavior when they are applying some environment, that is your spent acid, right? So what is the test solution? Basically carbon dioxide and nitrogen gas were injected through the liquid in and gas in tubes respectively. And what do we mean by the spent acid? So this is basically a reaction product of acids which contain 10% HCl, 1.5% HF, 3% HAC plus which they have just added few inhibitors, and then stratum rocks or some solid after acidizing fracture process. So before test, they just fill this full tube with this spent acid and then flow the gas. And if you would like to see the composition of tube, so here you can see the element and content. Chromium was 0.027%, silicon, manganese, phosphorus, sulfur, chromium, nickel, and others. So what was the experiment? We can understand the experiment by this plot here. So plot suggests, see in x-axis we have having a time. So basically they did the measurement for almost 190 hours, and the temperature was varying from 20 to 120. So the first step, they apply 7 MPa pressure of the nitrogen, and then at the 20 degrees Celsius for 120 hours, then there is a sudden jump in the temperature from 20 to 120 degree, and within the time of almost 20 hours. And then again they changed the pressure. It was from 7 MPa to 70 MPa with 1.2 MPa of the carbon and N2, otherwise other things was there. And then they just apply this pressure for almost more than 40 hours. Okay. So 120 hour temperature was 20 degrees Celsius with 7 MPa pressure, nitrogen gas, then 20 hour transition temperature. Then the inner pressure was elevated to 70 MPa with supplement of 1.2 MPa carbon dioxide and enough nitrogen gas. And the step third, the temperature was held at 120 degrees Celsius and the temperature was kept at 70 MPa. Finally, what they observed, the specimen fractured. When they applied this much temperature, this much load, they observed that the specimen fractured after 44 hours, holding a step at 3. So once it is fractured, then they have analyzed that fractured area, what kind of changes happened, what was the corrosion role there, and why such things was happened in case of that much load and conditions. So fracture position and morphology. So this is, you can see here the image of fracture surface. A is the fracture site and B is the fracture surface. So you can see this is the tube inside. If you're able to see here, this is the tube inside. So here you can see this is area is look like the fracture site, this area. So they have just dotted it, dotted area inside. They have zoomed it also. This is the dotted area. And this is the fracture surface. So in fracture surface, you have 3 different kind of surface. One is A area, where you can see these kind of semicircles are formed. See, are you able to see here? These 2 semicircles are formed here, here, and then if you see here, these 2 semicircles are there, right? And then there is a B region. B region is the second region. So where basically this forms, and then it look like it is going to go like this way, extended here from A to something C, right? It look like this. And then the C region. C region here, it's look like something, here something is initiated, goes like this way, and then something is fractured here in this region. So this C is a kind of fracture zone. So position in 6 meter long tube was there, right? So the tube fracture at 4 meter side coupling. So in coupling side, 4 meter it fractured. 2 semicircle morphology at A, B extended root as you see, and C basically is kind of necking character. So that we can easily see by just observing the our sample. But what was the reason why it is happening? So that we have to look out slightly more closer view. So fracture position and the morphology. So these three regions were analyzed by scanning electron microscopy, the micromorphology of the fracture surface, ABC corresponding to the area A. So A was one area, B is elongated area, and C is the necking area. Okay, and if you see these things, so the fracture originated from region A when the corrosion pit penetrate through the tube wall, right? Then extended quickly through region B and finally fractured at region C. So they analyze and they found like region A is the basic region or culprit where they started the formation of pit, and then pit basically penetrate through the tube wall. Inside it goes, form a big pit, and then it extended. You see in the region B earlier through the circle form, and then B, and then finally it reached to the region C and result in the fracture. So this was one analysis based on the morphology, and also the near crack region they have analyzed the surface and say that, see, this is the tube and this is the crack near the fracture surface. So see, these cracks are also there and they are basically following a kind of grains. So we can say there is an intergranular crack. So material tend to crack along the grain boundaries and shows intergranular fracture in feature. Okay, so they again go for more details. So the region which was looking like a circular, right? If you see the circular region, so see if they have gone for SEM analysis and they found that there is a three region. See, this is the pit and crack initiation zone. So this is very small. It look like there was a small crack. Maybe if you see the top surface, let's say if you are doing the top surface SEM, then you will be able to see only one spot. But if you see the cross section, so this is the cross section image. One spot is here, but it is extended like this way, right? It is extended like this way. So top it shows only this. So if you are seeing, let's say, top surface by optical microscope, you will not be able to understand what is the depth of this pit and what is the size of the pit. But if you see this, see how it's extended this, and that's why it calls for the such kind of fracture in the tube. And so therefore they are calling it a three region: pit and crack initiation zone, then crack propagation zone. So basically crack propagation zone is very big, and this is basic region, and it is going to help for cracking. And then crack tips, this is the crack tip. So pitting and crack zone, crack propagation zone, and then crack tip zone. And these are A, image B, C, D are the, so this is the first one, crack initiation zone. This is the second one, propagation zone, and this is the third one, crack tip zone. So here if you see the first one at the pitting zone or the crack initiation zone, even this is easily the pit form, so this is more likely to have corrosion, and therefore some byproducts are there. Therefore there is a very good contrast, and you are able to see these white black patches due to their formation of oxide and all. So it's not very conducting. Second and third is okay, but in case of third, you are able, if you see there is some cracks are there, so you can say there are some secondary cracks even inside there. So that was the big crack, and there are also another cracks are there. So that is basically the cause to form such kind of big crack in the system. So these kind of information can be extracted by doing the SEM analysis. Now we quickly move to the next topic, that is our transmission electron microscope. So if you see, the structure is again same, slightly few things are added. Our electron source, condenser lens, objective lens, intermediate lens, one more lens to analyze, then a specimen, and then projector lens. So basically here we are putting the specimen here, since we are going to see the transmitted one. Earlier we just see the reflected one or maybe the secondary electron in case of SCM. Here what is the idea? Let's say this is our sample, so what is transmitted here? And this transmitted one will go to the fluorescent sheet, and in fluorescent screen, whatever the amount of electron is there, depending upon that, this screen will become basically visible, and we can see the picture. So look like the shadow. Let's say you having the light putting on the sample, and then whatever you are able to see at the bottom. So that is the shadow, that is your TM, right? So 1 minute. So that is the shadow here. So same, what information we can get here? A crystal structure, very good information we can get by TM. That is even not possible by SCM and optical microscope. Dislocation and defect, grain boundaries, chemical analysis. If we are having some nanomaterials, then we can easily get the quality, the shape, size, and the density of the nanomaterials. And basically this transmitted electron will depend upon the thickness of the sample, and then electron transparency of the specimen, like how the electrons are interacting with the sample and what is the thickness of the sample. Both the things are going to control the number of transmitted electrons. And transmitted portion focused by the objective lens into a phosphorus screen, and then or maybe charge coupled device, CCD camera, and then we can generate an image in your computer. So this is another, here also we do electron diffraction. So electron diffraction, let's say you are having the incident beam here. This is our specimen. So if we are having the parallel beam of electron, and from specimen, if they interacted and your beam is scattered. So let's say this dot dot are the scattering lines. So again, by using objective lens, you can focus these scattered as well as your non-scattered. So this, they will be form the image plane. So here you are observing the image. This is your screen, right? But in between, if you see, there will be some region where your scattered beam will be separated as with respect to your incident beam. So this will give one idea about the scattering, and it can generate the image also with spot. So that is known as the electron diffraction. So back focal plane of the objective lens and where the diffraction pattern is found, this is the place. Now we'll see one data specimen. So before going to do the analysis in TM, one critical component is there, how we can prepare the specimen for TM, because in SCM we can just take 1 centimeter surface something and we can just load on the sample. But in TM, the primary requirement is your sample should be very thin, so that the electron beam should transmit through the sample. So the first condition is the specimen must be thin enough to transmit sufficient electron to form an image with minimum energy loss. A common sequence of preparation technique is ultrasonic disc cutting. So there's a tools. Then after cutting, you can do either dimpling or ion milling. So dimpling is basically a technique that produces a specimen with a thin center area and an outer rim of the sufficient thick to permit ease of handling. Means, let's say you are having a thick sample and then you just dish it. So what will happen? The edges will be thick, but this center portion will be thin. So you can just penetrate your beam from here and you can see what is in the sample. But in the ion milling, you can even just smooth out the surface and entire area you can make very thin. So both are possible, both kind of systems are there. You can see here one picture. So let's say we are having a sample, a steel sample, which is having some rust. So this black color is the rust, this black color. So just to protect the rust, because we are also willing to analyze the rust, how it is look like. So then top of, they just put the epoxy resin and then one cover glass slide. So this become like this way. Now you just cut it, right? You just cut it like this way. So if you will cut it, how it will look like? This portion only. This is your steel, rust. Then this is epoxy, and then this is glass. So now there's two process. Either we can do one thing, dimpler. So you just smooth out like this way so that we can get some idea about this material. We can transmit like this way. Otherwise, other is just by bombarding the ions, high energy ions, you can remove the sample and you can make it very thin. So it become very smooth and thin. So this is the ion milling. So by this way, you can prepare the sample and the loading and all already the job of operator. So now we'll see one example here. Then I will bind up the discussion. So corrosion measurement using TEM. Just one idea, like this paper you can follow. If the same paper, hector metal, which we have discussed earlier in case of SCM also, right? The effect of small content of chromium on wet, dry acid corrosion behavior of low alloy steel. The same paper. This is the, like, your sample is there where they have A, B, C, D, the four. So this is basically B, C, and D. What is the rust is there? So A is your sample. So if you are doing, so they are not much focused about the how this morphology and this. They are just trying to see what is the rust. Okay, what is the composition of rust? So they have just do the selected area electron diffraction so that you can get the pattern, and based on the pattern we can understand or identify which kind of material is there. So this is just steel structure. So they are just getting like kind of very well patterned dots. So it shows like it's kind of single crystal here, because you know that's only one crystal is there. But this is the rust. So in somewhere rust they did. So see, you are not able to see proper pattern, focused pattern. Why? Because it not having some proper angle, and your atom is having some mix compound. So therefore getting one dot, two dot, this dot, and then again some spots in between. So it shows like your structure is although single crystal but mix of single crystals. Here in case of C, see the pattern is not even defined. Something rough random. So it shows it's almost polycrystalline or kind of amorphous, not even polycrystalline also. Similar here in the D also. So what we can conclude, like by doing this, the rust is having almost the polycrystalline or the amorphous nature. It's not in the proper crystalline format of the single crystal. Sorry. And these are the composition. The rust is mainly composed of the several kind of ferric oxyhydroxide like FeOH, amorphous phases, FeOH and CFeOH. So basically the two different kind of phase, and all kind of FeOH are composed of FeOO6, but with different stacking sequence, because see, you are able to see the different kind of formation here. So the stacking sequence are also different. So if you just read this paper, you can get more detail how the TM can be analyzed. And I would also advise you just search one or two research article in which the TM analysis was given in detail for analyzing the corrosion product. So today I think I would stop my discussion. So what we talked today about the three techniques. One was the optical microscope. The second was the scanning electron microscope. So in optical microscope, we can get at least the larger size particles and surface analysis. In SCM, we can get also the cross-sectional analysis and of course the corrosion product analysis, what the morphology and size of the corrosion product and how these products basically associated with this material. In TM, slightly different information can be extracted, like crystal structure, what kind of material that can be also identified. And if the structure is very, very small, then also the morphology and the surface can be looked out. So thank you very much for today and soon. इस चर्चा में विभिन्न संदर्भ ग्रंथों से बहुत सारे चित्र और बिंदुओं को लिया गया है, जिनके लिए मैं आभार प्रकट करता हूं तथा आपके अमूल्य समय और इस चर्चा को सुनने के लिए बहुत बहुत धन्यवाद। पुनः नमस्कार, धन्यवाद।